people visit Alton Towers every year. They go there for the fun and the thrills, thrills which are designed to be safe. In fact, a leisure park like this is a zoo of different rides, and they're all based on the principles of Newtonian mechanics. So you can come here to have fun and to see mechanics in action.
Mechanics is about motion and its causes. And there's plenty of motion and plenty of interesting problems here.
Why do the chairs swing out as the speed increases? And why don't empty chairs swing wider than full ones? Now it's a vertical circle, but why don't the people fall out when they're upside down? Should you venture boldly or admit that you're scared? I don't think I'm going to like this. I really don't. Will you be sorry you had your second hot dog?
The real world is full of moving objects. Bodies in motion are everywhere. And what about sport? How should you throw to get the maximum range? And is there a best angle of throw? Eddie Kidd is someone who'd also like to get the maximum range. How many buses can he jump? And the calculations must be correct, which they weren't here in America with the Tacoma Narrows Bridge. Soon after it was opened, it was clear that something was wrong. In a wind, it began to sway and oscillate. In November 1940, only 4 months after the opening, the wind again blew in such a way that the oscillations became larger and larger. The result was inevitable. The calculations had been very wrong.
All these problems have one thing in common: motion. And thinking about motion began a very long time ago. In 300 BC in Greece, a man called Aristotle attempted to explain the phenomenon of motion. Why do bodies move, was the question. There can be no motion without a mover, was the answer from Aristotle. The mover supplies a force.
Clearly, force causes motion. The man pushes, the car moves. The force stops, the motion stops. The greater the force, the greater the motion. It seems reasonable, and Aristotle's ideas were accepted by people for almost 2,000 years. They were:
force causes motion. No force, no motion. The greater the force, the greater the motion. Force and motion are in the same direction. Well, okay so far, but what about this? What gives an ice hockey puck its motion? Obviously, the force of the stick. And what will give the stone its motion? Obviously, the force of the hand. But what keeps it going once the hand is let go and the force stops? Well, according to Aristotle, no force, no motion. But that's obviously wrong. Things do go on moving when there's no applied force. Lots of things. Now take this one. The greater the force, the greater the motion. Is this always right? We'll test it in a practical way with these two objects, a feather and a ball.
Once upon a time, there was a smart aleck cavalier who thought he knew all the answers to mechanics. He'd show them. A ball was heavier than a feather, so it would drop faster. Everyone had known this for 2,000 years. moment of truth.
Well, Aristotle seems to have got it right this time.
However, here's another even cleverer smart aleck Puritan who's going to show us that mechanics has moved on since Aristotle's time. You see, two balls, one heavier than the other. Now then, the heavier one will obviously land first, won't it?
No, Aristotle's wrong. They landed together, even though they had different weights. You'd think someone would have done that years before, but nobody had. Like all good experiments, it was just too simple. We're still doing these experiments to prove that Aristotle was wrong, but now they're done on the moon.
On the moon, where gravity is less than on the Earth, the weight of the hammer is still greater than the weight of the feather. The only difference is that here there's no air.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same
And when
time.
they're dropped, they do fall together.
So, Aristotle was wrong again. Now let's test Aristotle's third rule. What would he have said about the forces on a basketball if he'd known what a basketball was?
What Aristotle did say was that motion was in the same direction as the force. So, where's the force on the ball at these three positions? This is what Aristotle would say. A force is in the same direction as motion. But where has the force come from? It could be the force due to the thrower, but that disappears at the moment the ball leaves his hand. So that's not the force. And yet we can see that the ball goes in a curve. Now the only other force worth mentioning is its weight, the force of gravity acting on the ball, and that we know is downwards. So the motion here is not in the same direction as the force. Sorry, Aristotle.
The surprising thing is that it took so long for anyone to contradict him. But then he was looked up to as the expert on force and motion. It took another man, Isaac Newton, to finish these ideas off 2,000 years later. Isaac Newton was English. He went to Trinity College in Cambridge, and he thought about the motion of the planets. He was curious to find out why they move as they do. In 1687, he published the Principia, in which he wrote, in Latin, his ideas about force and motion. Newton proposed 3 laws of motion, and we're going to have a look at 2 of them. The first one was that
when no force acts on a body, it either remains at rest or moves with constant velocity.
Aristotle claimed that if no force acts on this ball, then it's at rest. But Newton disagreed with him. He said that if no force acts on this ball, then it's either at rest or moving with constant velocity. That's a constant speed in a certain direction. Have my ball back, please. Thank you. Now let's look at Newton's first law in practice.
The two teams here have been carefully matched, so that both are exerting the same pull. The link in the rope doesn't move, so Newton's first law says that there's no force acting. We know there actually are forces acting, but they're balanced. They act in opposite directions, and so cancel out. We say that there's no resultant force in any direction. But if they're not balanced, then there is a resultant force, and so movement. Quite a lot of it.
Here's another example. Why does the apple remain at rest? What forces are acting on it? Well, there's its weight acting downwards, but as the apple remains at rest, Newton's first law says there can't be a resultant force acting on it. So, W, its weight, must be balanced by the tension in the stalk, which pulls it upwards.
When no force acts on a body, it either remains at rest or moves with constant velocity. But what about the moves with constant velocity bit? What forces are acting on the stone when it's moving? Well, there's its weight, W, and the reaction upwards from the ice, N. But there's also friction, Fr. Friction acts in the opposite direction to the motion as it's trying to slow the stone down. As there's no motion vertically, Newton's first law says that N must balance W. So that leaves only Fr, the friction. And this will eventually bring the stone to rest. But what if the brushes could smooth the ice so much that the friction is reduced to nothing? Well then, Newton's first law says that the stone would keep on going forever with constant velocity until it hit the end of the rink. No force, you see, so no change of motion.
Think of it, if we could get up there, away from all the forces, there's nothing to prevent us going on with constant velocity forever. Forever. So Newton got it right with his first law. Now, his second law states that
if a force acts on a body, it causes the body to change its motion.
How did Newton establish his second law? Well, he spent a lot of time thinking about the motion of the moon around the Earth and the fall of an apple to the Earth. In each case, there's only one force acting, gravity, which is the pull of the Earth, but it has a different effect in the two cases. When the apple falls to Earth, its speed increases every second. But the moon doesn't fall down to Earth like the apple. It goes around the Earth in a circle. It's like this conker whirling round. You need the tension in the string to keep on changing its direction, and so keep it going in a circle, because if I let go, it flies off at a tangent.
Without a force on it, the moon too would go off at a tangent. But the force of gravity from the Earth makes it keep on changing its direction every second. Now imagine each of these steps being made shorter and shorter. And what you get is a circle. This is how Newton pictured it in his Principia.
So, for the apple falling and for the moon, or the conker, going round and round, the effect of the force is to cause a change in motion every second. For the apple, it causes a change in speed every second. And for the moon, or the conker, it causes a change in direction every second. And that's more or less how Newton arrived at his second law.
If a force acts on a body, it causes the body to change its motion every second.
What is this change in motion each second that Newton's on about? Well, we call it acceleration.
So force causes acceleration. F causes A. Or, to be more Newtonian, the effect of a force F on a body of mass m is to produce an acceleration A. And this is Newton's second law, one of the classic equations of all time.
But do Newton's laws really work? Let's apply the two laws here. Law 1. What are the forces on this car? Well, there's its weight, down, and the reaction from the ground, up. But as it doesn't lift off or sink into the ground, Newton's first law says these two must balance. So there's no resultant vertical force. There's a drag force, D, due to air resistance. But there's a much greater thrust force from the engine, T. And in comparison, drag can be ignored. So the resultant force is effectively only the thrust, T. That brings in Newton's second law. Here, the resultant force acting is the thrust T. And the effect of T is to cause an acceleration. So Newton's laws do work.
Here's a situation where air resistance certainly does matter. One of the Red Devils' free-fall parachute team giving us a demonstration. First of all, he accelerates. Why? Because he's falling, you'll say. True. And so the force down, his weight W, must be greater than the drag due to air resistance, D. The resultant force, W minus D, causes the acceleration. That's Newton's second law. But after a time, he doesn't get any faster. He's reached what's called terminal velocity. It's because the drag due to air resistance increases with speed and eventually balances the force due to his weight. So there's no resultant force, and therefore no acceleration, and therefore constant velocity, down to a safe landing.
Parachuting is a modern sport. Discus throwing, an ancient one. Newton's laws were in action long before he discovered them. In fact, Newton confirmed what the ancient Greek athletes knew from instinct, that the best angle to achieve maximum range is around about 45 degrees.
At t equals 0, he's launched at 22 metres per second at an angle A. You've had some time now at the terminals. What angle produces the greatest range?
45 degrees, sir.
Which means that at 22 metres per second and 45 degrees, he can go how far?
About 50 metres.
Well, we found if he goes at 200 metres per second, he'll clear the whole of the London transport fleet.
Eddie Kidd jumping over buses goes in an arc, but here there are loads of things which go round in circles or parts of circles, maybe horizontal or vertical or somewhere in between.
Circular motion can do some very strange things to you. In fact, circular motion is full of surprises, and it's full of problems to think about.
This is one of the models from a mechanics kit which has been specially designed to illustrate mechanics in action. Now this is like the corkscrew. It goes round and round, but it isn't quite as scary. And it can be used to solve this problem.
What is the critical height to loop the loop?
Well, what we do is we'll try it from a low height, first of all. Ooh. Hardly even got round the first loop, did it? Thank you. Let's try it from much further up. Well, that's sped round. So obviously the critical height is somewhere in between there and there. So what you do is you keep trying it at various heights. And I think you'll find that from here, it just goes round both of the loops. So that is the critical height. Now, over here is another model in our mechanics kit, and this one represents the beast. Now, I'll start the table turning. And when I do that, the forces acting on both of the counters are exactly the same as the forces acting on cars going round the beast. Now, if I speed the table up, watch what happens. The black counter slides off the table. So the conclusion from that is that a car can go faster on a banked piece of track without sliding outwards. Now, over here, we have another model which represents the chairoplane, the one with the chairs swinging round and round.
Here, there are at least two problems in the one machine. What happens to the angle as speed increases? And what is the maximum angle?
Well, let's increase the speed. As we increase it, the angle gets bigger and bigger until eventually it looks as though it's approaching the horizontal. I'm glad they don't do this at Alton Towers. "300 years ago, Newton started off thinking about force and motion by considering the movement of bodies here on Earth, like the fall of an apple, and the motion of heavenly bodies up there in space, like the moon. He proposed 3 laws of motion, and today we still use them. Here on Earth, like at Alton Towers, or up there in space, Newton's laws rule. Okay.